All right, welcome. Face today. Let's see here. Which is kind of fun, I guess. If you usually come on Zoom, then you just get to hear my voice. So here we're all in the same space, which is kind of nice. Okay, so yesterday we finished off and I kind of pounced a lot of ideas on you. And so what I want to do just for review, like the problem is I can see how laggy it is and it's very, very distracting. So anyways, I'll try not to be distracted. But so what I did was I just cropped out what we need out of this. It's very laggy. Sorry about that, guys. Oh, hey, good for you guys. That's awesome. Quite all right. Thank you for letting me know. Then welcome to everyone. So what I've done is, because for now, when we're talking about z-scores, we're only going to be concerned about the z-star line. And then just as a heads up, once we get into numerical data, then we're going to talk about t-scores. And so that's what the rest of the table is for, but we're going to use it in the same way. So we're going to learn those skills in this section, and then we're going to be able to use them later. Okay, so what I did was I just cropped out a little section of the t-table. So I could grab it like this. Okay. So what we want to do is just as a brief review, okay, I'm going to just sketch the curve, and just so we can see how we use this thing. And maybe before we talk about we said that before we talk about probabilities associated with the z-scores, how about we review the z-score? Right, so z is x minus mu over sigma. Okay, z is the number of standard deviations. I'll bump this down even more. Standard deviations. Standard deviations are denoted by sigma, lowercase sigma. An observation, which we denote by a lowercase x, is from the mean, mu. Yeah. And assuming x, and I guess I did a lower, I should do an uppercase, but x follows a normal distribution with a mean mu and a standard deviation sigma, right? So just as a reminder of this, this notation here. Okay. So in the questions that we have, we're going to be told that something follows a normal distribution or approximately normal, and then we'll have the mean and the standard deviation, and then we'll be able to calculate z-scores. And usually what we want to do is we want to find probabilities. Okay. So let's see here. All right. So. Oh. All right. Sounded like a question, but I think it was just an accidental unmute. All right. So let's see here. I shouldn't have brought this table in quite yet. In fact, maybe I'll just cut it out for a bit longer. Sorry about that, guys. I was so excited because I made that little crop version. We used z-scores. How do we use them? one to compare values from different normal distributions, right? That's one way that we can do it. We saw that with the SAT and the ACT scores, right? And so that's one way that we can use Z-scores. And so we use Z-scores, one, to compare observations from two different normal distributions. They don't even necessarily have to be different, but usually they are, okay? Normal distributions. All right, so for example, the SAT versus the ACT scores yesterday. And the second way that we are going to use Z-scores, and this is going to be the more prominent one coming up here, is to find probabilities associated with an observation. So to find probabilities associated with an observation. And that there looked like associated, but it's associated. All right, so now we're ready. So to find those probabilities, we're going to use a t-table, and that's only because when we're doing quizzes in class, you won't have access to software, and so we need something that we can use. There are calculators out there that can calculate these probabilities, right? And so, but I didn't want to force you to have to buy one. Sometimes they're a little bit expensive, so unless you already have one, I wouldn't recommend doing it, because there's lots of software that does it. You don't, so they don't have to be different, right? But often if they're from the same distribution, then you can just compare straight across, right? It's easy to say that, okay, well, someone, you can compare someone who's taller than another person, for example, right? But if you're comparing within the same group, whereas usually what we do is we want to talk about female heights versus male heights, who's taller within their respective groups, right? And so so usually they are different, but they don't have to be. And then I think the next question, so do we have to have two different distributions? And then the follow-up is, do they have to be normal distributions, I think is the follow-up, in order to use the Z-score. And the official answer is yes, they should follow a normal distribution. Sometimes we do it without it following the normal distribution. We just standardize things. But for us, it'll always be part of the question, right? It follows a normal distribution, so we're safe. But I standardize even if it's not normal sometimes, which is my answer. Well, I hear someone here. Oh, okay, it's okay. All right. Hopefully that maybe answered it. I don't know. Okay, so in order to find probabilities, we use software in real life. So that's why I want you to practice with using software. Okay, so R or Excel or just an online calculator, I don't really care how you do it. Okay, there's lots of online calculators. But so we use software in real life, but in class, we will use a table. Okay. Yeah, so the question is, if we're given the median for a distribution A, do we need to find the mean in order to find the z-score? Yes, in order to find the z-score, it does rely on having the mean. So you would have to find the mean and the standard deviation. Now, there are other standardizations that you could do using the median, but we're not going to do those. That's like beyond us. And so when we standardize, standardizing is really just finding the number of standard deviations from the mean something is, right? So what happens, and maybe we should visualize it, what happens is the first thing we're going to do is we have the distribution of X. And so here we have the distribution of X. So here we have X follows a normal distribution with a mean mu and a standard deviation sigma. So then here, right, the normal distribution, that's the shape, and then the mean mu and the standard deviation sigma. Yeah. Then what we do, if we have some value of X, so some observation here that we're interested in, right? If I want to find the probability of something larger than X, really what I want to find is this area above X, right? If I want to find the probability of being below X or less than X, then I would find this lower area. Okay? And so that's why even in the beginning, it's not gonna come naturally for you to draw the curve. I understand that, but just force yourself to draw the curve and try to visualize what the problem is asking for, because that's going to be really helpful later on, right? To have that skill and just to be able to draw it out, and then you would shade the area that you're interested in. So for example, if we're interested in maybe this area, right? The probability of being greater than X, then the next step that I do is I standardize X by using Z equals X minus mu over sigma. Oops. I'm trying to keep it all on this page here. Okay. And then what happens is I have this exact same curve. Okay, copy. But now Z follows a normal distribution centered on 1 with centered on 0 with a standard deviation of 1. And so now the only thing that changes here is that this is always 1, and this, sorry, I keep saying that wrong. And I don't know why, because mu is always 0, centered on 0. Okay. And then this X, all that's changed here is that this Z takes its place, right? And so the change here is from here to here. But the distribution stays the same. It's normal, but now it's standardized. So now it's on a 0, 1 scale, right? It's always centered on 0 and a spread of 1, right? And I don't mean the full spread, but we'll talk more about that. But just the standard deviation is 1. So now it's easy to talk about. Okay? But what we do, or why we do it, is because now I have this standardized scale that I can use to find this probability. Okay, so now we can use this using Z, we can find the probability. So like I said yesterday, we use that, I copied it and then I lost it, this one. We can use the t-table. And I know it's kind of confusing to use a t-table for Zs, but the reason we're doing it is because we have this line here. So for us, the only things that we're going to use for now, for today, and you can probably kind of link it to this top line, but for today, all I want to use are these two lines. So there are some kind of key cutoff points that I want to use. And so I want to draw a normal distribution. And I wonder if I could. No, not really. Not enough room. Draw this beautiful normal distribution. Hey, that's pretty good. Okay. So this is the Z curve. Z follows a normal distribution centered on 0 with a standard deviation of 1. And so here, first thing we know is that, okay, just as a fact, it's centered on 0. But we also remember that there's symmetry. Okay. And so now, even though I only have positive values of Z, right, Z star, you can ignore the star for a little bit, but what we have here, these are Z values. So I'm going to focus on a few, just kind of pick a few to jot down here. Maybe this one and this one. Oops. So I'm going to draw these on here. So let's see, 1.036, 1.960, and 3.091. Just remembering that this is a number line, and I'm starting with the positive values because we have the positive values in the table, right? But I'm also going to replicate these on the lower end. And oops, 3.091. Notice that I've chosen roughly 1, 2, 3, right? And so what we're going to see is that just as a fact, we can fit roughly 3 standard deviations on either side of the mean before the tails start closing in and become very, very, very small. Okay. And so what I'm going to do now is I'm going to map this. Let's see here. Right. The one-sided P just means the area in one of the tails, right? So whether it be the negative or the positive, it doesn't matter. And so I'm going to start there. And I'm going to draw here 1.036. And then how I kind of draw it, because if I'm shading, then I'm shading, and there's a lot of overlap and it can be hard to see. But I definitely started out shading the areas. So what I mean is maybe just going like this. Right, but I'm not going to do that because it gets too messy. So I just draw up and then kind of an arrow to show that this is the area that I'm talking about. And this area is 0.15. Okay, which means that this area is also 0.15 by symmetry. Okay, what does that mean in terms of probabilities? And I guess we'll just kind of call this the end of the review here. Otherwise, whole day is basically review, but more thorough. It's going to take a couple of passes. Okay, yeah, so what does that 0.15 mean? It means that the probability of a Z-score of 1.036 or larger, right? Or in other words, right, an observation being basically more than one standard deviation above the mean is 0.15, okay? And so same thing, the probability of an observation being less than one standard deviation above below the mean is also 0.15. Okay, and so it's not, you don't need the next line, right? But what it's saying is that, okay, if you care about both the tails, which we will later, right, then you could just say, okay, 0.15 plus 0.15 is 0.30, right? So that's all the two-sided P is doing. So it's not doing anything. The other thing, if we trace up to this confidence level, now we haven't talked about what the confidence level is or anything like that, but what I want to show you is that, okay, the confidence level is 70%. So what does that mean? Well, I can see here that this area in between is 70%. Yes, only applicable to the normal distributions. Yeah. So here in between, right, or 0.70, right, because I have 70% of the distribution, so of the normal distribution, is captured within one standard deviation-ish, right? It's 1.036, but when we talk about it, right, 70%. Okay. Because I have 0.15 plus 0.7 plus 0.15 makes 1, right? And so we're always relying on that fact that they have to add to 1. The total area is always 1. Okay. So same idea, if I color code the same way. So now if I move out to, let's say, basically 2 standard deviations away from the mean, right? So a Z-score of 2, 1.96 is, I would argue, close to 2, right? And so now I have, oops, now I have 0.025. So 2.5% in the upper tail and also 2.5% or 0.025 in the lower tail. I haven't scrolled up, so oh, so the symmetry, so the symmetry comes from the normal distribution. Okay, so so can a normal distribution with a mean 0 be asymmetric? No, because the normal distribution just is symmetric, right? So the definition of a normal distribution is that it's unimodal, so it has one peak and it's symmetric. And then oh, that's a good, so what does symmetry of data depend on? The data itself or the standard deviation? So it would depend on the data itself, rather where the data came from, the population the data came from, right? But a lot of things naturally follow a normal distribution. So that's why we're starting here. Oh, okay. So the mean of 0. So Z has a mean of 0, right? And that's just a fact, because what Z is saying, and yeah, you can have a mean of 0 if you have negative values and positive values. You can absolutely have a mean of 0. But in this case, Z is 0 because if the mean is 15, for example, then an observation of 15 is 0 standard deviations away from it, right? It doesn't matter what the standard deviation is, the distance 15 from 15 is 0, so then Z is 0. So that's why Z is now kind of shrunken down and centered on 0. So you can have a mean of 0 just from general data, but it would involve positive and negative values, right? Not just positive values, otherwise can't do it. Okay. Good. If you had to figure out what the yes, so here the mean is the center, so everything is symmetric around it, right? So on the lower end you have these negative values, so you're below the mean, and here you have these positive values on the right hand side, but it's exactly symmetric around 0. Okay, and also something to keep in mind is that means that this area is 0.50. I had to go a little bit kind of crooked there, but it's also nice, but it's also 0.5, right? So it's split in half, and so the area below the mean is 0.5 and the area above the mean is 0.5. Okay. Yeah, so if we had to figure out what percentage or proportion is between or within 2 standard deviations of the mean, right, then we have 0.025 and 0.025, so 0.05 or 5% are already taken up, and so the remainder here would be 95% or 0.95, which is exactly what it says up here. Okay, and so there are a lot of components here, and you don't need all of them, right? But once you kind of get the hang of it, they're all linked up. Okay, and so how we're going to use these probabilities in these areas, I like to think of it as a puzzle, right? So you've got this piece that you want, and you can take away a piece, you can add a piece, right? And there's lots of different ways that you can solve these problems. And so finally, right, for 3 standard deviations below and above the mean, right? Now we have a tiny area here, 0.001, and same thing on this side, 0.001, which means that we would have, oh boy, how much in between, right? If we kind of skip ahead, 3 standard deviations away from the mean. Essentially, we have 0.001 plus 0.001, that's 0.002. I'm going to go with 0.998. I'll have to check, but phew. So 99.8% or 0.998. There's kind of a quick rule of thumb that we usually introduce, and especially for real life applications, usually it's good enough to get a sense of probabilities using the empirical rule. And the empirical rule, we usually call it the 68, 95, 99.7 rule, and it's just a dirtier version of what we just did here. Okay, so let's start that. For quick approximations, you'll have this table. So this table, however much you want to use it or not, is up to you, but you'll have that table in a test. I'll print off a fresh one. Yeah. So for quick approximations of probabilities, we can use the empirical rule, which is also called the 68, 95, 95, 99.7 rule. Oops. And those are percentages. Okay. So we did roughly 1, roughly 2, roughly 3. And so if we just did 1, 2, 3, okay, then again, approximately what happens is that, okay, if I've gone mu, if I have mu minus sigma and mu plus sigma, so 1 standard deviation on either side of the mean, 1 standard deviation from mu, right? Then the area between here, a quick approximation. Oops, that was crooked. A quick approximation is that 68% of the data is within 1 standard deviation from the mean. Okay. And so here we have, let's see. Using the fact that you have the central 68% of the curve within 1 standard deviation of the mean, we can use that to find areas in the tails too, right? And so now I have 1 minus 0.68, but it has to be split evenly amongst the tails. Now I'm not going to go into detail. It's just something that you can work with. But we're going to use the table anyways, which is a little bit more detailed, but you absolutely can just use the 68, 95, 99.7 rule. Can you guess what the 95 is? Well, now we're going to move 2 standard deviations away from the mean, and that's what we did here, right? Ours is actually more precise that we exactly, right? So it's just 1, 2, 3, right? And so, and it's just a quick way to remember the areas under the curve. In fact, I've taught this course way back when at UBCO. I taught it one term. I guess I was bored or something and decided to change how I taught it. Just using the 68, 95, 99.7 rule, and then just using software for real approximations. Now we're going to do the same thing, but we'll have a table, so we'll have a little bit more to go off of. Okay, let's see here. Let's do kind of a different color. Mu minus 2 sigma and then mu plus 2 sigma. So now I have 2 standard deviations from the mean. Notice that you're talking about the central, now 95% of the curve. Which we saw before. And then finally, let's do, I think, mu minus 3 sigma and mu plus 3 sigma. Which is 3 standard deviations from mu. And as an approximation, we use 99.7, right? Kind of weird, 68, 95, 99.7. But if you say it enough, then it just kind of sticks. So that's what we use, 99.7%. So these are just approximations, right? But if you've calculated a Z-score, do you mean where I've drawn these lines? Because it's supposed to be equal, but it's just to visualize. And so I don't spend a lot of time kind of spacing out my lines because I said that they're the same. They're not visually, but that's because I'm sloppy. And whenever we draw these curves, it's just to help us visualize a problem. So it's not super important. Right. Oh, haha. Okay. Okay. So the reason is because this 68, 95, 99.7 relates to the area under the curve. So the drop, right? So here we're at the peak and the area under the curve is quite large, right? And then so here the area is decreasing, right? And so it's not going to be a square. Usually we want to think about areas in terms of a square, but it's not, or a rectangle maybe. But instead, right, when we have this curvature, we need to remember that, okay, moving 1.5 standard deviations away, it's actually not going to be easy to calculate this area because it's going to be halfway, and it's part of it is sloped, right? So it's not really intuitive, and so that's why we have these guidelines, right? 68, 95, 99.7, or more precisely, right, we can use that table. Okay. Sounds good. Have a great weekend. Okay, so let's see here. We can use these areas, right, these probabilities, to find probabilities associated with an observation. We can also work the other way. I call it working backwards. Okay, and so we can also use the probabilities to work backwards, is what I usually call it, to find an observation that satisfies some probability or proportion, right? So find, or maybe I should say an observation that satisfies a specific probability. So let's see here. Do I have an example? Let me just make sure. Okay. Just write out this example. Based on a sample of 100 men, the heights of male adults in the US are nearly normal. the heights of male adults, oops, in the US is nearly normal with a mean of 70 inches. And I'm not very good with inches, but it's okay. Usually I ignore the units, and I know that's bad, but in most cases we can just ignore the units. And standard deviation 3.3 inches. Let's say Eric, stealing from this, Eric's height is, and let me just grab, is at the 20th percentile. How tall is he? Oh, let's see here. Okay, yes, so it's really important. So the question is about these values, the 68, 95, 99.7. So it's really important that when we talk about these probabilities, right, or these percentages, then we're talking about the area under the curve, right? And so so the area under this curve is 68% of the 100%. Right, so 68% of all the data or all the population is within one standard deviation. And then you move out to 2 standard deviations. Now you've captured the central 95%. Then you move up 3 standard deviations, and you've basically captured the entire population within 3 standard deviations of the mean, right? 99.7%. There's some in the tails, right? Because the tails never close. But yeah, so it's really important. It's just the area under the curve. Awesome. Okay, so now first thing we notice is that, okay, nice, it's nearly normal, so I can start off and I can draw a curve. So as soon as you see nearly normal, I want you to just draw a curve, see what happens, right? And then start putting information on there. And that is difficult in the beginning, right? But it takes practice. And then we're told that it's nearly normal with a mean of 70 and a standard deviation of 3.3. So I'm just going to put sigma as 3.3, and maybe I'll use mu. Usually I don't write the mu, but it's among our first examples anyways. So okay, so now instead of being given, okay, Eric is 75 inches tall, right? What's the probability of finding someone taller than Eric, right? That's one way that we could ask this question. But now we're told that Eric's height is at the 20th percentile. Or maybe, you know what? For a little extra practice, I'm going to change that to the 80th. You'll see why I did that, maybe. Okay. What does the 80th percentile mean? It means that 80% of the population is below it, right? Or 80% of the distribution. So 80% of the distribution is below it, is below his height. but let's work it out. So let's see here. So the 80th percentile, first thing I'm going to do is I'm going to say, okay, well, I know it's above the mean. Why? Because it's more than 50%, right? And so, like I said, again, it doesn't really matter where you draw this, but you're going to force this area, now I will shade it, to be 0.80. So that area is 0.80. That's what you're forcing. Now, what we want to find is, okay, well, what value of x makes that happen? Okay. And so how we're going to do this, right? And I'm going to use the table. I'm not going to use the 68, 95, 99.7 rule for this. I'm going to use the table. But what I'm going to do is I'm going to say, okay, well, that means that this area must be 0.2. So then what can I do? Okay, well, I can use the fact that, okay, well, I don't know what the value of x is, but I do know the value of z that forces 0.2 in the upper tail, right? How can I do that? I can, right? So here, I'm forcing 0.2 in the upper tail, which means that here I am, right? So a Z of 0.841 forces an area of 0.2 in the upper tail. Okay. If I had kept this at the 20th percentile, right, and I am choosing values that are in the table, so I'll make sure that I do the same, but if I had kept this at the 20th percentile, that's fine, you can solve that too, right? It would just be 0.2 here, but then this value you would have to make a negative, right? Because it's below the mean. And I'm almost out of time, but what this means is that, okay, I've got, so then Z is 0.841. And the mean was 70 and the standard deviation was 3.3. So now we need to solve for x. So Z is x minus mu over sigma. I'm going to do it in general, but then I'll show you, or you'll see it's on your formula sheet, right? Z times sigma plus mu equals x. Usually I don't write it so sloppy, but here I am. So x in this case is 0.841 times 3.3 plus 70. And I am out of time, so I'll fill it in once I've calculated. But now you'll be able to do those assignment questions. And we haven't had a lot of practice, so I'll start with an example next day. But try that assignment that I posted. It's pretty fun once you get the hang of it. And I guess have a great weekend. All right. Oh, thank you. I'm going to jot that down. 72.7753 is how tall he is. Nice. All right. Have a great weekend. And I'll see you guys again on Tuesday, but in class.